Right now, as you read these words, the particles that make up your body are doing something that should be impossible. They're existing in multiple states at once, being in several places simultaneously, and only deciding where they actually are when something observes them. This isn't science fiction or mystical thinking. It's the fundamental nature of reality at the smallest scales, and it's happening inside you, around you, and through you at this very moment. Perhaps you've heard that quantum mechanics is strange, that it defies common sense, that even Einstein called it spooky. But what if I told you that the weirdness goes deeper than you've imagined? What if the very act of reading these words, of being conscious of them, is collapsing infinite possibilities into the single reality you're experiencing right now? Tonight, we're going to journey into the quantum realm, not the Hollywood version with shrinking suits and dramatic music, but the real quantum world that's far stranger than any movie could portray. We'll explore the experiment that broke physics, meet particles that refuse to choose a single identity, and confront the uncomfortable possibility that reality itself might not exist until someone looks at it. Take a moment to look at your hand. It seems solid, doesn't it? Defined edges, clear boundaries, definitely there. But zoom in far enough, past cells, past molecules, past atoms, and you'll find mostly empty space, populated by probability clouds, particles that aren't really particles, waves that aren't really waves, things that exist in a state of maybe until the universe forces them to make a choice. Are you ready to question everything you thought you knew about reality? Good, because by the end of this journey, you might not be sure if you're reading this story, or if this story is reading you. For most of human history, reality seemed straightforward. Things were either here or there. Cats were either alive or dead. Doors were either open or closed. This was the world of classical physics, where Newton's laws reigned supreme and everything made intuitive sense. In this classical world, if you knew the position and velocity of every particle in the universe, you could, in principle, calculate the entire future and past. The universe was like a vast clockwork machine, predictable and deterministic. Cause led to effect in an unbroken chain stretching from the Big Bang to the heat death of the universe. Scientists of the 19th century were so confident in this worldview that Lord Kelvin famously declared in 1900 that physics was essentially complete, with only two small clouds on the horizon. Those two small clouds would become the hurricanes of relativity and quantum mechanics, devastating the comfortable certainties of classical physics. The quantum revolution began quietly, with Max Planck trying to solve a seemingly minor problem about black body radiation, why hot objects glow the colors they do. The classical physics prediction was absurd. It suggested that hot objects should emit infinite energy at ultraviolet wavelengths, something called the ultraviolet catastrophe. Planck's solution was radical, though he didn't fully realize it at the time. He proposed that energy isn't continuous, but comes in discrete packets, quanta, like a staircase rather than a ramp. Energy could only exist at certain levels, not in between. This was December 14, 1900, now considered the birthday of quantum mechanics. But Planck thought his quanta were just a mathematical trick, not a description of reality. It would take a young patent clerk named Albert Einstein to suggest that quanta were real, that light itself came in particles, later called photons. This earned Einstein his Nobel Prize, not for relativity, but for explaining the photoelectric effect using quantum ideas. Light, it turned out, was having an identity crisis. Sometimes it behaved like a wave, spreading out, creating interference patterns, diffracting around obstacles. Other times it behaved like a particle, colliding with electrons, being absorbed and emitted in discrete packets. It wasn't either a wave or a particle, it was somehow both. This wave-particle duality was weird enough when confined to light. But in 1924, Louis de Broglie made an audacious suggestion. If light waves could be particles, perhaps particles could be waves. He proposed that all matter, electrons, atoms, even baseballs and planets, had wave properties. The wavelength of these matter waves was inversely proportional to momentum. For large objects like baseballs, the wavelength was impossibly small, which is why we don't see baseballs diffracting around obstacles. But for electrons, the wavelength was measurable, and experiments soon confirmed that electrons could indeed create interference patterns like waves. This wasn't just particles acting like waves. Sometimes, it was deeper. The electron wasn't a particle that moved in a wave pattern. It was the wave, spread out through space, until measurement collapsed it to a point. Reality at the quantum scale wasn't made of things but of possibilities. Imagine you have a barrier with two narrow slits cut into it. Behind the barrier is a screen that can detect where things hit it. Now, shine a light through the slits. What pattern would you expect on the screen? If light is made of particles, you'd expect two bright lines corresponding to the two slits, like bullets fired through two windows. If light is a wave, you'd expect an interference pattern, multiple bright and dark bands created by waves from the two slits, constructively and destructively interfering with each other. When we actually do this experiment with light, we see the interference pattern, waves it is, then. But here's where things get weird. We can dim the light source until we're sending one photon at a time. Each photon hits the screen at a specific spot, like a particle. But as we send more and more individual photons, they build up the same interference pattern. Think about what this means. Single photon traveling alone somehow goes through both slits simultaneously and interferes with itself. It's not that half the photon goes through one slit and half through the other. The entire photon, whatever that means, passes through both slits as a wave of possibility. But it gets weirder. Let's say we want to know which slit each photon goes through. We set up detectors at the slits to tell us. The moment we do this, the interference pattern disappears. Now we get two simple bands, as if the photons are particles going through one slit or the other, never both. The act of measuring which path the photon takes forces it to take a definite path. Without measurement, it takes all possible paths. The photon somehow knows whether we're watching and changes its behavior accordingly. This isn't a quirk of our measurement, disturbing the system. Even if we use the gentlest possible detection method, even if we detect which slit the photon went through after it's already passed through, but before it hits the screen, the interference pattern still disappears. The photon's history, which slit it went through, isn't determined until we measure it, and that measurement retroactively determines what happened. If this were just about photons, maybe we could dismiss it as something special about light. But in 1927, Clinton Davison and Lester Germer showed that electrons also create interference patterns. The double-slit experiment works with electrons, atoms, even molecules as large as buckyballs, 60 carbon atoms. In 2019, researchers at the University of Vienna performed the double-slit experiment with molecules containing up to 2,000 atoms, objects large enough to see with a good microscope. These molecules, when not observed, pass through both slits simultaneously and interfere with themselves. Where is the boundary? How big does something have to be before it stops being quantum and starts being classical? This is called the measurement problem. And after a century of quantum mechanics, we still don't have a satisfying answer. The double-slit experiment introduces us to superposition, the ability of quantum systems to exist in multiple states simultaneously. An electron isn't just at position A or position B, it's in a superposition of being at both positions, and everywhere in between, until measurement forces it to choose. This isn't just about position. Particles can be in superposition of different energy states, different spin orientations, different velocities. The quantum world is a world of and rather than or. Particles are spinning clockwise and counterclockwise, excited and ground state, here and there, all at the same time. Erwin Schrödinger described this with his famous wave function, a mathematical entity that describes all possible states of a quantum system and their probabilities. The wave function doesn't tell you where a particle is, it tells you the probability of finding it at any given location if you look. But what is the wave function? Is it real, like an electromagnetic field, or is it just a mathematical tool for calculating probabilities? This question divides physicists to this day. Some say the wave function is reality. We live in a multiverse of possibilities described by an ever-evolving wave function. Others say it's just information, a description of what we might find if we measure. The wave function evolves according to the Schrödinger equation, smoothly and predictably. But when we measure the system, the wave function collapses instantly to a single state. This collapse is random. We can predict probabilities, but not outcomes. Einstein hated this, saying God does not play dice with the universe. But experiment after experiment confirms that at the quantum level, God does indeed play dice. The role of observation in quantum mechanics is perhaps its most disturbing feature. In classical physics, observation is passive. We watch events unfold without affecting them, at least in principle. But in quantum mechanics, observation is an active participant in creating reality. When we say observation causes wave function collapse, what exactly do we mean? Does it require a conscious observer, a human, any living thing, or just any physical interaction that could, in principle, reveal information about the system? This question has spawned numerous interpretations. The Copenhagen interpretation, Bohr and Heisenberg. The wave function isn't real. It's just a tool for predicting measurements. Reality doesn't exist in a definite state until measured. This is the most common interpretation, but it's philosophically unsatisfying. It divides the world into quantum systems and classical observers without explaining the boundary. The many worlds interpretation, Hugh Everett. Every quantum possibility actually happens in parallel universes. When you measure a particle's position, you don't collapse the wave function, you entangle with it. There's a version of you seeing each possible outcome in different branches of the multiverse. No collapse, no special role for observation, but an infinity of parallel realities. Consciousness causes collapse, von Neumann-Wigner. Consciousness is what collapses the wave function. Without conscious observation, the universe remains in superposition. This gives consciousness a fundamental role in physics, but raises awkward questions about what counts as conscious and what happened before conscious beings evolved. Objective collapse theories. Penrose, Giraldo. The wave function collapses spontaneously when systems get too large or complex. No observation needed. Quantum mechanics is an approximation that breaks down at larger scales. So preserves realism, but requires modifying quantum mechanics in ways not yet detected. Entanglement, spooky action, at a distance. In 1935, Einstein, Podolsky, and Rosen EPR proposed a thought experiment meant to show that quantum mechanics must be incomplete. They imagined two particles created together in a way that their properties were correlated. If one was spin-up, the other must be spin-down. According to quantum mechanics, neither particle has a definite spin until measured. They exist in superposition, but the instant you measure one particle and find it spin-up, you know the other is spin-down, no matter how far apart they are. The measurement of one instantly affects the other. Einstein called this spooky action at a distance and argued it was absurd. He believed particles must have definite properties before measurement, hidden variables, and quantum mechanics was just ignorant of these properties. But in 1964, John Stuart Bell proved that if hidden variables existed, they must violate locality. Influences must travel faster than light. Bell's inequality provided a way to test whether nature uses hidden variables or genuine quantum superposition. Experiment after experiment has violated Bell's inequality, confirming quantum mechanics. When particles are entangled, measuring one instantly affects the other, regardless of distance. In 2017, Chinese scientists demonstrated entanglement between particles separated by 1,200 kilometers using a satellite link. This doesn't allow faster-than-light communication. The correlation only appears when you compare measurements, which requires classical communication. But it does mean that reality is fundamentally non-local. The universe isn't made of separate objects interacting. It's a unified whole where everything is connected to everything else. One of quantum mechanics' strangest predictions is that observation can freeze evolution. If you measure a quantum system frequently enough, it never changes state. This is called the quantum Zeno effect, after Zeno's paradox about motion being impossible. Imagine an atom that can decay radioactively. Quantum mechanics says there's a probability it will decay in any given time period. But if you keep checking whether it's decayed, measuring it constantly, you reset its wave function each time. The atom never gets a chance to evolve into the decayed state. This has been experimentally confirmed. In 1990, researchers at NIST trapped ions and showed that frequent measurements could suppress their transitions between energy states. The more often they measured, the less likely transitions became. This raises profound questions about the nature of time and change. Is change only possible when we're not looking? Does the universe need privacy to evolve? Some researchers even suggest that consciousness might use the quantum Zeno effect to maintain stable states in the brain, though this remains highly speculative. The measurement problem is the dirty secret of quantum mechanics. Despite the theory's incredible success, it's the most accurately tested theory in science. We don't understand its most basic feature, measurement. What exactly happens when we measure a quantum system? The mathematics says the wave function collapses instantly from superposition to a definite state. But how? Why? What physical process causes this collapse? The problem is that measurement seems to require different rules than normal quantum evolution. Between measurements, quantum systems evolve smoothly according to the Schrödinger equation: deterministic, reversible, linear. But measurement is sudden, random, irreversible. It's as if the universe has two different sets of laws, one for when we're not looking, and one for when we are. Consider Schrödinger's famous cat thought experiment. A cat is placed in a box with a quantum device that has a 50% chance of releasing poison. According to quantum mechanics, until we open the box, the cat is in superposition, both alive and dead simultaneously. This seems absurd for a cat, but where do we draw the line? Electrons can be in superposition, atoms can be in superposition, even large molecules can be in superposition. Why not cats? And if cats can be in superposition, why do we never see them that way? One partial answer is decoherence. Any quantum system interacting with its environment quickly loses its quantum properties. The environment, air molecules, photons, cosmic rays, constantly measures the system, collapsing superpositions. For a single electron in a vacuum, decoherence is slow. But for a cat, with its billions of atoms all interacting with air, thermal radiation, and each other, decoherence happens in about 10 circumflex 23 seconds, far too fast to observe. This explains why we don't see quantum effects at human scales. The bigger something is, the harder it is to isolate from the environment, the faster it decoheres. The classical world emerges from the quantum through environmental interaction. But decoherence doesn't fully solve the measurement problem. It explains why we don't see superposition at large scales, but not why measurement gives definite outcomes rather than just different superpositions. The fundamental question remains: what picks one possibility from the many? Where does quantum end and classical begin? This boundary question has practical implications as technology pushes into the quantum realm. Modern experiments have created quantum superposition in increasingly large objects. 2010, a visible barely mechanical resonator. In superposition 2019, molecules with 2,000 atoms, showing interference. 2020, tardigrades, microscopic animals, possibly in superposition. Disputed. Proposed experiments aim to put even larger objects in superposition, viruses in superposition, suspended nanoparticles in superposition, eventually, perhaps, living cells. Each success pushes the boundary further, suggesting there might be no fundamental limit. Perhaps everything can be quantum, if isolated enough from environmental decoherence. This raises the possibility that even macroscopic objects could display quantum behavior under the right conditions. The many worlds interpretation, MWI, takes quantum mechanics at face value. The wave function never collapses, it just keeps evolving. When you measure a particle's position, you don't force it to choose one location. Instead, you entangle with it, and the combined system, U plus particle, evolves into superposition. In one branch, you see the particle at position A. In another branch, another version of you sees it at position B. Both branches are equally real. The universe constantly splits into parallel realities, one for each possible outcome of every quantum event. This sounds insane, but it's actually the most conservative interpretation. It adds nothing to the mathematics of quantum mechanics. No collapse, no hidden variables, no special role for consciousness, just the Schrödinger equation, applied universally. The implications are staggering. Every possible history happens somewhere. There are branches where dinosaurs never went extinct, where you made different life choices, where history unfolded differently. The number of branches is mind-boggling. Every particle interaction creates new branches, exponentially multiplying realities. Critics argue this is too extravagant, creating infinite unobservable worlds to explain our one observed world. Proponents counter that the alternatives are worse, adding mysterious collapses or hidden variables. The debate continues, with prominent physicists on both sides. Perhaps reality isn't made of particles or waves but information. This it from bit hypothesis, proposed by John Wheeler, suggests that physical properties are answers to yes-no questions, binary information. In this view, quantum mechanics is fundamentally about information. Superposition is information in multiple states. Entanglement is shared information. Measurement is information extraction. The uncertainty principle limits information availability. Quantum information theory has practical applications. Quantum computing, using superposition and entanglement for parallel processing. Quantum cryptography, using entanglement for unbreakable encryption. Quantum teleportation, transferring quantum states using entanglement. These technologies work, suggesting information might be more fundamental than matter or energy. Reality might be computational, with the universe as a vast quantum computer calculating its own evolution. The role of consciousness in quantum mechanics remains contentious. Some argue consciousness is necessary for collapse. Others say it's irrelevant. But intriguing connections exist. Quantum biology, quantum effects in biological systems, uses quantum coherence for efficient energy transfer. Bird navigation might use quantum entanglement in cryptochrome protein. Smell might involve quantum tunneling in olfactory receptors. DNA mutation might involve quantum tunneling of protons. Quantum cognition, quantum models of human decision-making. Superposition of thoughts before decision. Entanglement between concepts. Interference between competing ideas. Collapse to definite choice upon decision. Orchestrated objective reduction. Penrose and Hameroff propose consciousness arises from quantum processes in brain microtubules. Controversial but not definitively disproven. These connections don't prove consciousness is quantum, but they suggest quantum mechanics might be relevant to understanding mind and life. The delayed choice quantum eraser experiment takes the double-slit weirdness to another level. We can measure which slit a photon went through, destroying the interference pattern. But if we then erase that information before looking at the pattern, interference returns. The weird part, we can make the choice to erase or not after the photon has already hit the screen. Our future decision seems to determine the photon's past behavior. The photon must somehow know whether we'll erase the which path information. This doesn't allow sending information to the past. The pattern only appears when we correlate measurements, requiring classical communication, but it suggests the past isn't fixed until the future measurements that would reveal it are complete. The Elitzur-Vaidman bomb test is a thought experiment turned real. Imagine bombs triggered by a single photon. Can you determine if a bomb is functional without triggering it? Classically, no, you'd have to send a photon which would trigger a functional bomb, but quantum mechanically, you can use interference. Send a photon through a Mach-Zehnder interferometer with the bomb in one path. If the bomb is functional, it could detect the photon collapsing superposition. This changes the interference pattern even if the bomb doesn't trigger. With repeated tests, you can determine with near certainty whether the bomb works without ever triggering it. You gain information about a path the photon didn't take, interaction-free measurement. This has practical applications in imaging light-sensitive materials without damaging them. It also raises philosophical questions about what constitutes interaction and observation. Current experiments push quantum superposition to larger scales. Levitated nanoparticles, silica spheres containing millions of atoms levitated by laser light in vacuum. Cooled to near absolute zero, they enter quantum ground state. Proposals exist to create superposition of different positions, superconducting quantum interference devices, SIXWIDs, rings of superconductor, carrying current in both directions simultaneously, billions of electrons in superposition, optomechanical systems, mirrors weighing picograms in superposition of different positions, visible barely to naked eye. The goal: create superposition in objects large enough to test whether gravity causes wave function collapse, as some theories predict. If successful, we might see quantum effects at human observable scales. Quantum computers use superposition and entanglement for computation. A classical bit is either 0 or 1. A quantum bit qubit can be both simultaneously. N qubits can represent two circumflex end states simultaneously, enabling massive parallelism. Potential applications: breaking current encryption Shor's algorithm, simulating quantum systems for drug discovery, optimizing complex systems logistics, finance, machine learning, with exponential speedup. Current challenges: maintaining coherence. Quantum states are fragile. Error correction: quantum errors are continuous, not discrete. Scaling up: current computers have approximately 100 qubits, need millions for useful applications. Companies like IBM, Google, and Rigetti offer cloud access to quantum computers. Google claimed quantum supremacy in 2019, performing a calculation impossible for classical computers. Quantum sensors use superposition and entanglement for unprecedented precision. Atomic clocks, using superposition of atomic states for timekeeping accurate to 1 second in 33 billion years. Gravitational wave detectors, LIGO uses quantum noise reduction to detect space-time ripples from colliding black holes. Quantum magnetometers, detecting single electron spins for medical imaging and navigation. Quantum radar, using entangled photons to detect stealth aircraft working even through jamming. These sensors approach the fundamental limits of measurements set by quantum mechanics itself. Quantum key distribution uses entanglement for provably secure communication. Any eavesdropping disturbs quantum states, alerting legitimate users. China has launched quantum satellites and built thousands of kilometers of quantum communication networks. Future possibilities: quantum internet connecting quantum computers, distributed quantum computing, quantum cloud services, blind quantum computing, using others' quantum computers without revealing your data. Quantum mechanics forces us to reconsider reality's nature. Realism: do properties exist before measurement? Quantum mechanics suggests no. Properties are created by measurement, not revealed by it. Locality: can influences travel faster than light? Entanglement shows correlations that seem non-local, though they can't transmit information. Determinism: is the future determined by the present? Quantum randomness suggests fundamental indeterminacy in nature. Objectivity: does reality exist independently of observation? The observer effect suggests observation partially creates reality. These aren't just philosophical musings, they affect how we interpret experiments and develop theories. Does quantum randomness enable free will? Some argue pro-quantum indeterminacy breaks the chain of classical determinism, creating room for free will. Quantum random events aren't free will, they're just random. Free will requires control, not randomness. Synthesis. Perhaps consciousness can bias quantum probabilities without violating physical laws, influencing outcomes within the range of quantum uncertainty. This remains highly speculative, but quantum mechanics at least breaks classical determinism's stranglehold on free will debates. If reality is fundamentally information-based and probabilistic, are we living in a simulation? Quantum mechanics might support this. Wave function collapse resembles computational optimization. Planck scale suggests pixelated space-time. Quantum mechanics might be compression algorithm for simulating reality. Counterarguments. Quantum mechanics is continuous, not discrete. Like computation, no evidence of simulation glitches or boundaries. The simulation hypothesis is unfalsifiable. The debate continues, with quantum mechanics providing ammunition for both sides. I first encountered quantum mechanics in high school physics, and my initial reaction was disbelief. Surely the teacher was exaggerating. Particles in two places at once, reality depending on observation. It sounded like mysticism, not science, but the experiments were undeniable. The double-slit experiment, which I later performed myself with a laser and hair strands, showed interference patterns that shouldn't exist if reality was what I thought. The equations worked, predicting experimental results to extraordinary precision. The more I learned, the stranger it became. Bell's inequality violations, quantum erasers, interaction-free measurements, each seemed impossible, yet experiments confirmed them. Reality was far stranger than I'd imagined. What struck me most was how quantum mechanics challenges our basic assumptions. We assume objects have definite properties, causes precede effects, observation is passive. Quantum mechanics violates all these assumptions, yet it works better than any theory in history. Quantum mechanics has changed how I see the world, not in a mystical quantum consciousness way, but in recognizing that reality is fundamentally uncertain, interconnected, and observer-dependent. This has practical implications, embracing uncertainty as fundamental, not just lack of knowledge, recognizing interconnection. Everything affects everything else, understanding that observation changes what's observed, accepting multiple perspectives as equally valid. It's also deeply humbling. If our basic intuitions about reality are wrong at the quantum level, what else might we be wrong about? How many of our assumptions about consciousness, life, and existence might be equally misguided? Despite its strangeness, or perhaps because of it, quantum mechanics has a peculiar beauty. The mathematics is elegant, the experiments are ingenious, and the implications are profound. There's something poetic about reality being made of possibilities, only becoming definite when observed, about particles being connected across vast distances, about observation creating reality rather than just revealing it. Quantum mechanics suggests the universe is far more interesting than classical physics implied, not a clockwork machine, but a creative unfolding of possibilities, not separate objects interacting but an interconnected whole, not fixed and determined but open and participatory. We're discovering quantum effects throughout biology. Photosynthesis. Plants use quantum coherence to efficiently transport energy, maintaining superposition for surprisingly long times in warm, wet conditions. Enzyme catalysis, quantum tunneling, allows enzymes to catalyze reactions that would be impossible classically. DNA mutation, proton tunneling might cause spontaneous mutations, making evolution itself quantum mechanical. Consciousness, controversial but not impossible. The brain might use quantum effects for computation or experience. These discoveries suggest life exploits quantum mechanics in ways we're only beginning to understand. The biggest unsolved problem in physics is reconciling quantum mechanics with general relativity. They give different descriptions of reality. Quantum mechanics reality is probabilistic, non-local, observer-dependent general relativity. Reality is deterministic, local, observer-independent. Proposed solutions include string theory. Elementary particles are vibrating strings in higher dimensions. Loop quantum gravity. Space-time itself is quantized at Planck scale. Emergent space-time. Space and time emerge from more fundamental quantum entities, resolving This conflict might reveal whether quantum mechanics is fundamental or emergent, whether space-time is continuous or discrete, whether information or geometry is more basic. Applying quantum mechanics to the entire universe raises profound questions. Wave function of the universe. Does the universe have a wave function? Who observes it to cause collapse? Quantum origin. Did the universe begin in quantum superposition? Did observation cause the Big Bang? Multiverse. Does cosmological wave function branching create parallel universes? Anthropic principle. Do we exist because we're in the branch where conditions allow observers? These questions push quantum mechanics to its limits, where physics meets metaphysics. After a century, we still don't know what the wave function is. Ontic real. The wave function is a physical entity, like an electromagnetic field. But what kind of entity exists in configuration space rather than physical space? Epistemic. Knowledge. The wave function represents our information about the system. But then what determines actual properties? Nomological law-like. The wave function is a law of nature, not an entity. But laws usually govern things. What does this law govern? Structural relational. The wave function describes relationships between possible measurements. But relationships between what? Each interpretation has problems. The question remains open. Why probabilities? Why does quantum mechanics only predict probabilities, not definite outcomes? Possible answers. Fundamental randomness. Nature is inherently probabilistic at the quantum level. Hidden variables. Definite values exist, but are inaccessible to us. Many worlds. All outcomes occur. Probabilities reflect which branch we'll find ourselves in. Consciousness selection. Consciousness selects from quantum possibilities. Information limits. Probabilities reflect fundamental limits on information availability. The Born rule gives probabilities as the square of wave function amplitude, but we don't know why this rule, rather than another. Einstein believed quantum mechanics was incomplete, missing hidden variables that would restore determinism and locality. Bell's theorem showed local hidden variables are impossible, but non-local hidden variables remain possible. Alternatives to quantum mechanics. Bohmian mechanics. Particles have definite positions guided by a pilot wave, Guillardua theory. Wave functions spontaneously collapse at random intervals. Quantum information theory. Reality is fundamentally information, not waves or particles. Each alternative makes slightly different predictions, potentially testable with future experiments. Understanding quantum mechanics offers practical insights. Embrace uncertainty. Uncertainty isn't just ignorance. It's fundamental. Perfect prediction is impossible in principle, not just practice. Everything is connected. Entanglement shows that separate objects are abstractions. Reality is interconnected, in ways we're only beginning to understand. Observation matters. The act of observing changes what's observed. This applies beyond physics. Attention shapes reality. Multiple possibilities. Before measurement, all possibilities coexist. Keep options open until observation forces choice. Context. Dependence. Properties depend on measurement context. The same system gives different answers to different questions. Quantum thinking. Quantum mechanics suggests new ways of thinking. Complementarity. Wave-particle duality. Shows that contradictory descriptions can both be true. Apply this to other paradoxes. Superposition. Hold multiple ideas simultaneously without choosing. Let them interfere and create new patterns. Entanglement. Recognize deep connections between apparently separate things. Change one. Change all. Uncertainty. Relations. You can't know everything simultaneously. Choosing what to measure means choosing what to ignore. Observer participation. You're not separate from what you observe. Your questions partially determine the answers. The quantum attitude. Living with quantum mechanics cultivates certain attitudes. Humility. Our intuitions about reality are wrong. What else might we be wrong about? Wonder. Reality is stranger than we imagined. The universe is more interesting than classical physics suggested. Openness. Multiple interpretations are possible. Hold beliefs lightly. Participation. We're not passive observers, but active participants in reality's unfolding. Mystery. Some questions might not have answers, or the answers might be stranger than the questions. After exploring quantum mechanics' strange landscape, we return to the fundamental question: what does it mean that reality behaves this way? Perhaps it means reality is more fluid than solid, more possibility than actuality, more process than thing, more information than matter, more observation than existence. Or perhaps these are just human categories, imposed on something beyond categories. Quantum mechanics works perfectly for prediction and technology, but its interpretation remains mysterious. We can calculate but not comprehend. We can use but not understand. Maybe quantum mechanics shows the limits of human understanding. Our brains evolved to navigate the classical world of medium-sized objects at medium speeds. Quantum mechanics describes a realm outside our evolutionary experience. We're like fish, trying to understand water, using concepts from a world we can't fully escape. Our languages, logics, and intuitions are classical. We're trying to understand the quantum using classical concepts, like describing color to someone who's never seen. Perhaps full understanding requires transcending human cognitive limitations, or perhaps the universe is fundamentally stranger than any mind can comprehend. Quantum mechanics is nearly a century old, yet the revolution continues. Each experiment reveals new strangeness. Each application opens new possibilities. Each interpretation raises new questions. We're still in the early days of the quantum age. Just as the steam engine preceded thermodynamics understanding, we're using quantum mechanics before fully understanding it. Future generations might look back at our confusion with amusement, having developed new concepts we can't imagine. Or perhaps the mystery is permanent. Perhaps reality is fundamentally inexplicable, and quantum mechanics is our first glimpse of this inexplicability. Perhaps the universe isn't meant to be understood, only experienced and explored. Studying quantum mechanics has profoundly altered my worldview, not in a new age quantum healing way, but in recognizing that reality's foundations are nothing like everyday experience suggests. I've become more comfortable with paradox, accepting that contradictory things can both be true. Uncertainty, embracing not knowing as fundamental, not failure. Interconnection, seeing separation as approximation, not reality possibility. Holding multiple options without premature collapse. Participation, recognizing my role in shaping what I observe. It's also made me more skeptical of certainty. If our basic assumptions about reality are wrong, what else might we be mistaken about? How many obvious truths are just artifacts of our limited perspective? Learning quantum mechanics is an emotional roller coaster. Confusion, initial encounter with concepts that violate common sense. Particles in two places, reality depending on observation. The brain rebels. Frustration, the mathematics works. Experiments confirm it, but understanding remains elusive. You can calculate what happens but not why. Or gradually realizing the universe is far stranger and more wonderful than imagined. Reality is not mundane machinery, but creative mystery. Vertigo, feeling the solid ground of classical reality dissolve into quantum uncertainty. Everything you thought was solid is mostly empty space and possibility. Wonder, eventually reaching a state of appreciative bewilderment. The universe is weird, and that's beautiful. How do you live knowing reality is quantum? For me, it means holding things lightly. Properties, beliefs, identities, all are more fluid than they appear. Nothing is as solid or permanent as it seems. Expecting surprises. If particles can tunnel through barriers and be in two places at once, what surprises might life hold? Appreciating mystery. Not everything needs explanation. Some things are more beautiful mysterious than explained. Recognizing participation. I'm not separate from the universe observing it. I'm part of it, helping create what I observe. embracing both, and moving beyond either, turning to both. And light is waves and particles. I am individual and interconnected. Quantum computers will revolutionize medicine, simulating molecules for drug discovery, understanding protein folding, personalized medicine based on quantum biology, materials, designing room temperature superconductors, creating materials with programmed properties, revolutionizing energy storage. AI quantum machine learning could create AI that truly understands rather than just pattern matches. Climate, optimizing carbon capture, designing better solar cells, simulating climate with unprecedented accuracy, but also threats. Cryptography, current encryption will be broken. New quantum-safe methods needed. Privacy, quantum sensors could detect things we thought undetectable. Inequality, quantum advantage might create unbridgeable technological gaps. Warfare, quantum radar, quantum hacking, perhaps even quantum weapons. A quantum economy is emerging. Investment, billions flowing into quantum startups, countries racing for quantum supremacy. Jobs, quantum programmers, quantum ethicists, new careers emerging. Industry, quantum sensors in smartphones, quantum random number generators for security, quantum optimization for logistics. Education, universities creating quantum programs, online quantum courses proliferating, quantum literacy becoming important. This revolution will be as transformative as the digital revolution, perhaps more so. Nations are recognizing quantum technology as strategically crucial. China, massive investment in quantum communication, launching quantum satellites, building quantum networks. USA, National Quantum Initiative, quantum research centers, military quantum programs. Europe, quantum flagship program, focus on quantum sensors and simulators. Others, Canada, Japan, Australia, Russia, India, all developing quantum strategies. Quantum technology might determine future global power balances. Countries without quantum capabilities might be left behind, like those that missed the Industrial Revolution. Quantum mechanics forces us to reconsider existence itself. Objects, are there really separate objects, or just patterns in the universal wave function? Properties, do things have properties, or do properties emerge from measurement? Space, is space fundamental, or does it emerge from entanglement? Time, does time flow, or is it emergent from quantum correlations? Causation, does cause precede effect, or can future measurements determine past properties? These aren't just philosophical games. Different answers lead to different physics theories. Quantum mechanics raises questions about consciousness. The hard problem. How does subjective experience arise from objective physics? Quantum mechanics makes this harder by making the objective uncertain. Panpsychism. If observation is fundamental to physics, is some form of awareness fundamental to reality? Free will. Does quantum indeterminacy create room for free will, or is randomness just as constraining as determinism? Identity. If many worlds is true, which branch is you? Are all branches equally you? Death. In many worlds, there are always branches where you survive. Does some version of you experience quantum immortality? These questions remain open. At the intersection of physics and philosophy, quantum mechanics suggests information might be reality's foundation. Ephraim Wheeler proposed that all physical entities are information theoretic in origin. Digital physics. Perhaps reality is computational, with quantum mechanics as the operating system. Holographic principle. All information in a volume might be encoded on its surface, suggesting space is emergent. Quantum Darwinism. Classical reality might emerge from quantum through information selection and amplification. If information is fundamental, consciousness, as information processing, might be more fundamental than currently believed. Apply quantum principles to decisions. Superposition. Before deciding, hold all options in superposition. Let them interfere, creating new possibilities you hadn't considered. Measurement. Recognize that observing options changes them. The act of analysis affects what you're analyzing. Entanglement. Understand that decisions aren't isolated. Each choice entangles with others, creating correlations across your life. Uncertainty. Accept that you can't know all consequences. Optimize for robustness rather than prediction. Collapse. Once decided, commit fully. Half-hearted action is like partial measurement, neither here nor there. Use quantum principles for creativity. Wave function. Let ideas exist as possibility clouds before forcing them into specific forms. Interference. Allow different ideas to interfere, creating unexpected patterns and combinations. Tunneling. Sometimes solutions tunnel through barriers that seemed insurmountable. Non-locality. Draw connections between apparently unrelated things. Everything influences everything. Observer effect. Notice how your perspective shapes what you create. Change perspective. Change creation. Quantum relationships. Apply quantum insights to relationships. Entanglement. Recognize deep connections beneath surface separation. What affects one affects all. Complementarity. People show different aspects depending on context, like wave-particle duality. Uncertainty. You can't know everything about someone. Choosing what to observe determines what you see. Superposition. People exist in multiple states simultaneously. Happy and sad. Strong and vulnerable. Measurement problem. Observing someone changes them. Your attention shapes who they become. The 2020s will see. Quantum advantage. Quantum computers solving real problems. Classical computers can't. Quantum internet. First quantum networks connecting cities, then countries. Quantum sensors. In smartphones, cars, medical devices. Quantum becoming everyday. Quantum biology. Understanding life's quantum foundations, leading to new medicine. Quantum AI. Machine learning, enhanced by quantum processings. The next century, by 2124, we might have room temperature quantum computers, no more dilution refrigerators, quantum laptops possible, quantum medicine, drugs designed using quantum simulation, treatments using quantum effects, quantum engineering, materials with programmed quantum properties, metamaterials that seem magical. Quantum consciousness, understanding if how consciousness uses quantum effects. Quantum cosmology, experimental tests of universe's quantum origin. Eventually, humanity might master quantum reality, manipulate quantum effects, as easily as we now use electricity, transcend classical limits, break free from classical constraints on computation, communication, sensing, merge with quantum, brain-computer interfaces that are quantum, not classical. Explore quantum dimensions, access to dimensions or realities currently hidden. Become quantum evolution or enhancement, making us naturally quantum coherent. These possibilities sound like science fiction, but so did computers, flight, and space travel. Quantum mechanics invites us to question everything. What if reality is nothing like it appears? What if consciousness plays a fundamental role? What if everything is connected in ways we can't see? What if multiple realities exist simultaneously? What if the universe is participatory, not objective? These aren't questions with easy answers. They're invitations to wonder, to explore, to remain curious about the nature of existence. Quantum mechanics gives us permission to not know. The greatest physicists don't fully understand it. Feynman said, "Nobody understands quantum mechanics." This isn't failure, it's honesty about mystery's depth. In a culture obsessed with certainty, quantum mechanics says uncertainty is fundamental. In a world of binary choices, it offers superposition. In an age of isolation, it reveals entanglement. After a century of quantum mechanics, the wonder hasn't diminished. Each answer reveals new questions. Each experiment opens new mysteries. Each application suggests new possibilities. We're like children who found a door to a vast playground. We've explored the entrance, played with some toys, but most of the playground remains undiscovered. The quantum realm stretches before us, infinite with possibility. We began with this question, and after our quantum journey, what's the answer? Reality is probabilistic, not deterministic, participatory, not objective, interconnected, not separate, informational, not just material, mysterious, not mechanical. But these are just words, classical concepts trying to capture something beyond classical description. Reality is what it is, regardless of our descriptions. Quantum mechanics is our best current map, but the map is not the territory. Quantum mechanics is a gift to humanity, not just technological, though quantum computers, sensors, and communication will transform civilization. The deeper gift is philosophical and spiritual. Quantum mechanics shows us the universe is far stranger than we imagined. Our intuitions about reality are limited. Mystery is fundamental, not temporary. We're participants, not just observers. Everything is connected in ways we're only beginning to glimpse. It's a gift of humility and wonder, showing us how much we don't know and how magnificent the unknown is. Ultimately, quantum mechanics is a mirror. It reflects our assumptions, revealing their limitations. It shows us that reality doesn't conform to our expectations, but exceeds them in ways we couldn't imagine. Looking into this mirror, we see our classical prejudices about how things should work, our discomfort with uncertainty and paradox, our desire for simple, intuitive explanations, our assumption that we're separate from what we observe, our belief that reality exists independently of observation. The mirror doesn't show reality as it is. That might be impossible. It shows us ourselves trying to understand reality, and in that reflection, we learn both about the universe and about the nature of understanding itself. Our journey through quantum mechanics ends where it began, with wonder at reality's strange nature. But the real journey is just beginning. Every day, experimentalists probe deeper into the quantum realm. Theorists develop new interpretations. Technologists build quantum devices. Philosophers grapple with implications. And you, having read this, are now part of this journey. You've glimpsed the quantum realm's strangeness. You've seen how observation shapes reality, how particles exist in multiple states, how everything is mysteriously connected. You can never fully return to the classical worldview. This knowledge brings responsibility. As quantum technologies emerge, informed citizens must guide their development. As quantum insights spread, we must distinguish genuine implications from quantum mysticism. As reality's nature is revealed as stranger than imagined, we must remain grounded while embracing wonder. We stand at the dawn of the quantum age. The 20th century discovered quantum mechanics. The 21st century is applying it. The 22nd century might master it. We're among the first generations to know that reality is quantum, to build quantum devices, to glimpse quantum truth. Future generations might take quantum reality for granted, like we take electricity for granted. But we live in the special time of discovery and wonder, when the quantum realm is still new, still surprising, still revolutionary. What a time to be alive, when humanity is discovering that reality is far stranger, far more interesting, far more mysterious than our ancestors dreamed. So when we're learning that we're not passive observers but active participants in reality's unfolding, when we're realizing that the universe is not a machine but something far more wonderful, a creative, probabilistic, interconnected, participatory mystery. As we close, one question remains. If reality is this strange at the quantum level, what other strangeness awaits discovery? What assumptions about consciousness, life, time, space, existence itself will future discoveries overturn? Quantum mechanics taught us that reality doesn't match our intuitions. It's a lesson in humility and wonder. If particles can be in two places at once, if observation creates reality, if everything is entangled, what else might be possible? Perhaps consciousness is fundamental, not emergent. Perhaps time is illusion, not reality. Perhaps space is projection, not foundation. Perhaps existence itself is stranger than we can imagine. The quantum revolution isn't ending, it's just beginning. We've opened a door to a universe far stranger than classical physics imagined. We've glimpsed the quantum realm, but vast territories remain unexplored. Saying, here's my invitation to you. Don't just learn about quantum mechanics, let it change how you see reality. Let it open your mind to possibilities you hadn't imagined. Let it humble your certainties and expand your wonder. Question your assumptions about what's real, what's possible, what's connected. Embrace uncertainty as fundamental, not failure. See yourself as participant, not just observer. Recognize the mystery at reality's heart. And remember, you are made of quantum particles. You are a quantum system. The strangeness we've explored isn't separate from you. It is you. You are superposition collapsed into specific form. You are entangled with everything. You are possibility made actual by observation. You are the universe observing itself, creating itself through observation. You are quantum mechanics in action. Strange, mysterious, wonderful. The particles that make you were forged in stars, traveled across space, assembled into you through quantum processes we're only beginning to understand. You are stardust organized by quantum mechanics into consciousness, into awareness, into wonder, at your own quantum nature. Reality is not what it seems. It's far stranger, far more interesting, far more participatory than classical physics suggested. Quantum mechanics isn't just a theory about tiny particles, it's a revelation about reality's nature, including our own nature. We are quantum beings in a quantum universe, just beginning to understand what that means. The journey of discovery stretches before us, infinite, with possibility, strange beyond imagination, wonderful beyond words. Welcome to quantum reality. It's stranger than you thought, it's more connected than you imagined. It's more mysterious than you dreamed, and you're part of it. Not just observing but participating, not just learning but creating, not just discovering but becoming. The quantum revolution has begun. Reality will never be the same, neither will you. Welcome to the quantum age. Welcome to the real world. Stranger, more wonderful, more mysterious than any dream. The observation has been made. The wave function has collapsed. This moment, reading these words, is your quantum reality. What will you do with this knowledge? How will it change you? What possibilities will you explore? For decades, biologists assumed quantum effects couldn't survive in the warm, wet, noisy environment of living cells. Quantum coherence, they believed, required isolation, cold temperatures, perfect stillness. Life seemed too messy for quantum mechanics. They were wrong, spectacularly wrong. The revolution began with photosynthesis. When plants capture sunlight, the energy must travel from the chlorophyll molecule that absorbs it to the reaction center, where it's converted to chemical energy. This journey through a forest of proteins should be inefficient, the energy bouncing randomly until it maybe finds its target. But plants achieve near-perfect efficiency. 95% of captured photons successfully deliver their energy. How? The answer stunned physicists. Quantum coherence. The energy doesn't choose one path. It explores all possible paths simultaneously through quantum superposition. Like a quantum computer solving a maze, it finds the optimal route by trying all routes at once. Even more remarkably, this quantum coherence persists for hundreds of femtoseconds at room temperature, an eternity in quantum terms. Plants have somehow evolved to maintain quantum states in conditions that should destroy them instantly. They've solved a problem that quantum computer engineers struggle with using sophisticated technology. The mechanism appears to involve vibrational assistance. The protein environment vibrates in specific ways that actually protect quantum coherence rather than destroying it. It's like juggling in an earthquake, where the shaking somehow helps keep the balls in the air. Evolution discovered quantum engineering billions of years before humans discovered quantum mechanics. How do you smell? The conventional theory said it was all about molecular shape. Molecules fit into receptors like keys and locks. But this lock and key model couldn't explain some puzzling observations. Why do molecules with identical shapes sometimes smell completely different? Why do molecules with different shapes sometimes smell identical? Luca Turin proposed a radical alternative. The nose might be a quantum device detecting molecular vibrations through electron tunneling. When a molecule binds to a receptor, electrons can tunnel across it, but only if the molecule's vibrational frequency matches the energy gap. Different vibrations mean different smells. This quantum theory explains the shape paradox. Molecules with the same shape but different atomic compositions vibrate differently. Molecules with different shapes might vibrate similarly. The nose isn't feeling molecular shapes, it's listening to molecular songs. Experiments support this. Flies can distinguish between hydrogen and deuterium versions of the same molecule. Identical shapes, different vibrations. Humans can smell the difference too. Our noses might be quantum spectrometers, using electron tunneling to detect molecular vibrations at the quantum level. DNA replication is remarkably accurate. Errors occur only once per billion base pairs. But those rare errors, mutations, drive evolution. We've assumed mutations were classical, cosmic rays breaking bonds, chemicals causing damage, copying errors from thermal fluctuations. But quantum mechanics might play a crucial role. Protons in DNA base pairs can quantum tunnel between positions, temporarily creating wrong base pairings. Usually these return to normal before replication, but occasionally the quantum state collapses into a mutation. This has profound implications. If mutations are partly quantum, they're not purely random. Quantum tunneling rates depend on environmental factors, temperature, electromagnetic fields, chemical conditions. Evolution might be more responsive to environmental conditions than pure randomness would suggest. Some researchers go further, suggesting quantum coherence might allow DNA to sample multiple mutations simultaneously, collapsing to beneficial ones more often than chance would predict. This remains highly speculative, but if true, it would mean evolution itself is a quantum process. The most controversial application of quantum mechanics to biology is consciousness. Several theories propose quantum processes in the brain, orchestrated objective reduction, Penrose and Hameroff, suggest consciousness arises from quantum computations in microtubules, protein structures inside neurons. They propose that quantum coherence in microtubules creates conscious moments when the wave function spontaneously collapses. Critics argue the brain is too warm and noisy for quantum coherence, but supporters point to evidence. Microtubules have properties that might support quantum states anesthetics, which eliminate consciousness, affect microtubule dynamics. The time scale of conscious moments, approximately 40 Hz, matches predicted collapse times quantum information theory of consciousness. This proposes consciousness as integrated information, and quantum entanglement might enable the kind of information integration required for consciousness. The brain might use quantum processes not for computation, but for binding distributed information into unified conscious experience. Quantum cognition. Even if the brain isn't quantum, human, decision-making shows quantum-like properties. Order effects. Answer depends on question order. Interference. Conflicting thoughts can amplify or cancel. Entanglement. Correlated beliefs that change together. Superposition. Holding contradictory beliefs simultaneously. These might be classical processes that mathematically resemble quantum mechanics, or they might reflect deeper quantum processes we haven't detected yet. Quantum sensors are already entering everyday life, though most people don't realize it. Your smartphone might soon contain quantum magnetometers. Using nitrogen vacancy centers in diamond, these can detect magnetic fields 1,000,000 times weaker than Earth's field. Applications include medical scanning without MRI machines, navigation without GPS, detection of underground pipes and cables, brain-computer interfaces, reading neural activity, quantum accelerometers, using atom interferometry. These measure acceleration with extraordinary precision. They could provide navigation in GPS-denied environments, detection of underground resources, earthquake early warning, gravitational mapping, quantum cameras, single-photon detectors approaching quantum limits of sensitivity, night vision in near-total darkness, 3D imaging through fog and smoke, seeing around corners using scattered light, medical imaging with minimal radiation. The quantum internet won't replace the classical internet, but will add a quantum layer enabling unhackable communication. Quantum key distribution ensures any eavesdropping is detectable. China's quantum satellite Messias has demonstrated this over thousands of kilometers. Distributed quantum computing. Link quantum computers worldwide, creating virtual quantum computers more powerful than any single machine. Quantum cloud services. Access quantum computers remotely, without revealing your computation. Blind quantum computing preserves privacy even from the quantum computer operator. Clock synchronization. Synchronize clocks worldwide to femtosecond precision, enabling better GPS accuracy. Coordinated telescope arrays acting as Earth-sized instruments. Financial transaction timing preventing manipulation. Fundamental physics tests requiring precise timing. Quantum sensing networks. Distributed quantum sensors could detect dark matter passing through Earth. Monitor seismic activity globally. Track climate change with unprecedented precision. Search for signs of life on exoplanets. Quantum mechanics is enabling materials with properties that seem like magic. Topological insulators. Materials that are insulators inside but conductors on their surface. The surface conduction is topologically protected, immune to defects and impurities. Applications include quantum computers resistant to errors, highly efficient electronics, spintronics using electron spin for computation, novel sensors and energy devices, time crystals, structures that repeat in time rather than space, maintaining perpetual motion without energy input. Discovered in 2016, they challenge our understanding of thermodynamics. Potential applications: quantum memory lasting indefinitely, ultra-precise timekeeping, quantum sensors of unprecedented sensitivity, perpetual motion at the quantum scale, though not violating thermodynamics. Metamaterials, structures with properties not found in nature. Negative refractive index, enabling invisibility cloaks. Perfect lenses beating the diffraction limit. Acoustic metamaterials controlling sound like light. Quantum metamaterials controlling quantum states. High temperature, superconductors, materials conducting electricity without resistance at relatively high temperatures, still cold, but achievable with liquid nitrogen rather than liquid helium. Understanding their quantum mechanics could lead to room temperature superconductors revolutionizing energy. Levitating trains without expensive cooling. Quantum computers operating at higher temperatures. Lossless power transmission. Quantum mechanics suggests information is more fundamental than we thought, leading to paradoxes. The black hole information paradox. When matter falls into a black hole, its quantum information seems to disappear when the black hole evaporates through Hawking radiation, but quantum mechanics says information must be preserved. Solutions propose information is encoded on the black hole's surface. Holographic principle. Information escapes in subtle correlations in Hawking radiation. Black holes leave remnants preserving information. Information escapes through wormholes. This paradox forces us to reconsider what information is and whether it's truly fundamental. The measurement information paradox. Measurement extracts information from quantum systems, but where does this information come from? The system, the measuring device, the interaction. This relates to the deeper question of what constitutes measurement. Wojcicki quantum Darwinism proposes that classical reality emerges through a selection process. The environment constantly measures quantum systems, but only certain states survive this observation to become classical reality. The process works like this. Quantum systems interact with environments. Information about certain states proliferates through the environment. These fit states become objective reality. Other states remain quantum, unobserved. This explains why we all see the same classical reality. Despite quantum uncertainty, the environment selects and amplifies certain quantum states, creating consensus reality through information natural selection. Implications. Objectivity is emergent, not fundamental. Reality is what survives environmental selection. Different environments might select different realities. Consciousness might influence selection through observation. Carlo Rovelli's relational quantum mechanics takes observer dependence to its logical conclusion. Properties only exist relative to observers. There's no absolute state of a system, only states relative to other systems. In this view, no observer-independent reality exists. Every physical system can be an observer. Properties arise from interactions, not inherent existence. Reality is a network of relationships, not objects. This radically relational view suggests asking what really happened is meaningless without specifying observer. Different observers can have incompatible but equally valid descriptions. Reality is perspective all the way down. The universe is information about relationships, not things. Cubism interprets quantum probabilities as subjective beliefs rather than objective chances. The wave function doesn't describe reality, but an agent's beliefs about future experiences. Key ideas: quantum states are personal, not universal. Measurement is personal experience, not objective event. Wave function collapse is belief update, not physical process. Quantum mechanics is a user's manual for agents, not reality's description. This solves measurement problem by denying there's an objective process to explain, but it raises questions. Why do personal beliefs follow quantum rules? How do different agents coordinate their realities? What exists independently of agents? Researchers are pushing quantum effects to ever larger scales. Quantum drums, mechanical resonators, visible to naked eye, have been put in superposition. A drum simultaneously vibrating and not vibrating. Schrödinger's drum, living Schrödinger's cats. Proposals to put living organisms in superposition. Bacteria in superposition of locations. Tardigrades, surviving quantum superposition. Eventually, perhaps, conscious observers. Gravitational quantum effects, testing whether gravity causes wave function, collapse, particles in superposition, creating superposed gravitational fields, testing if mass limit exists for quantum superposition, probing quantum gravity without reaching Planck's scale. Quantum mechanics challenges our understanding of time. Quantum time crystals, structures repeating in time without energy input, challenging thermodynamics' second law, though not violating it due to clever physics. Negative time quantum systems can have negative dwell times, spending negative time in certain regions, not time travel, but another quantum paradox. Quantum clocks, using entanglement to create clocks, surpassing classical limits, detecting time dilation from millimeter height differences, measuring gravitational waves' effect on time, testing if time itself is quantized in definite causal order. Quantum superposition of causal orders. A causes B and B causes A simultaneously, implemented in quantum circuits, offering computational advantages. Classical thermodynamics assumes many particles, but what about single quantum particles? Maxwell's demon realized, using quantum information to extract work from heat, seemingly violating thermodynamics' second law. Resolution. Information processing has thermodynamic cost. Quantum engines, single atoms as engines, extracting work from quantum coherence. Classical limits running on entanglement as fuel, extracting work from quantum measurements. Quantum refrigerators, cooling below classical limits, using quantum effects. Algorithmic cooling, using quantum computation. Cooling by measurement and feedback, approaching absolute zero, asymptotically. Thermodynamic uncertainty relations, trade-offs between precision and dissipation. More precise engines dissipate more energy. Fundamental limits on efficiency. Countries recognize quantum technology as strategically crucial. China's quantum leap, $15 billion National Laboratory for Quantum Information Sciences. Quantum satellite Messius, demonstrating space-based quantum communication 2,000 km. Quantum communication network, Beijing, Shanghai, claims of quantum advantage in specific problems. American Quantum Initiative, $1.2 billion. Federal funding, over 5 years. National Quantum Coordination Office partnerships between government, industry, academia, focus on quantum computing and networking. European quantum flagship, €1 billion, over 10 years. Focus on quantum communication, computing, simulation, sensing, building quantum internet infrastructure, emphasis on quantum software and applications. Other players: Canada, early leader in quantum computing. D-Wave, Xanadu, Japan, focus on quantum materials and sensors. Australia, silicon-based quantum computing. Israel, quantum software and algorithms. India, Russia, South Korea, significant investments beginning. The quantum revolution needs quantum literate workers. Education revolution. Universities, creating quantum engineering programs. Online, quantum computing courses, reaching millions. High schools, introducing quantum concepts. Quantum games teaching quantum mechanics. Skills gap, shortage of quantum engineers and programmers. Need for quantum-aware business leaders. Requirement for quantum ethicists and policymakers. Demand for quantum science communicators. Democratizing quantum, cloud access to quantum computers. Open source, quantum software. Qiskit, Cirq, Q-hash, quantum hackathons and competitions. Community-driven, quantum education, quantum ethics and governance. Quantum technology raises ethical questions, privacy concerns. Quantum computers, breaking current encryption. Quantum sensors, detecting previously undetectable. Quantum surveillance possibilities. Need for quantum safe cryptography. Security issues. Quantum hacking capabilities. Quantum warfare potential. Protecting quantum infrastructure, preventing quantum terrorism. Equality questions. Quantum divide between nations. Access to quantum resources. Quantum technology, increasing inequality, ensuring quantum benefits reach everyone. Governance challenges, regulating quantum technology. International quantum agreements, preventing quantum arms race. Balancing innovation with safety. You can observe quantum effects at home. Polarization experiments. Use polarizing sunglasses to explore photon polarization. Stack polarizers to see quantum effects. Demonstrate wave-particle duality with simple materials. Interference patterns. Create double-slit interference with laser pointer and hair. Observe thin film interference in soap bubbles. See quantum colors in oil slicks. Quantum eraser. Simple quantum eraser with polarizers. Demonstrate retroactive determination. Show measurement affecting past tunneling. Observations. LEDI demonstrates quantum tunneling. Tunnel diode shows negative resistance. Scanning, tunneling, microscope images. Online, quantum thinking exercises, mental exercises, exploring quantum concepts. Superposition, meditation. Hold contradictory thoughts simultaneously. Feel multiple emotions without choosing. Exist in uncertainty, without resolution. Entanglement, awareness. Notice connections between apparently separate things. Feel how changing one thing changes others. Recognize non-local correlations in life. Observer effect practice. Notice how observation changes what you observe. See how attention shapes reality. Recognize participation in creation. Uncertainty, acceptance. Embrace not knowing as fundamental. Let go of need for definite answers. Find peace in probability. Living quantum principles. Apply quantum insights to daily life. Morning superposition. Start day, holding multiple possibilities before collapsing into specific plans. Quantum decisions. Let options interfere, creating new possibilities through combination. Entangled relationships. Recognize deep connections. How affecting one affects all. Uncertainty navigation. Move forward despite incomplete information. Trusting quantum uncertainty. Observer participation. Consciously choose what to observe. Knowing observation shapes outcome. A civilization. Mastering quantum mechanics might. Quantum architecture. Buildings using quantum materials. Structures in superposition. Until observed. Quantum tunneling transportation. Entangled infrastructure. quantum economics, quantum money impossible, to counterfeit superposition, economic states, entangled markets responding instantly. Quantum game theory optimization, quantum governance, quantum voting ensuring privacy and verifiability, superposition of policies until measurement entangled decision-making, quantum democracy, quantum art, artworks existing in superposition, entangled performances across distance, quantum music using superposition, observer-dependent art, post-quantum physics, what lies beyond quantum mechanics, theories of quantum gravity, string theory, vibrating strings in higher dimensions, loop quantum gravity, quantized space-time causal sets, space-time as discrete points, emergent gravity, gravity, from entanglement, beyond quantum mechanics, post-quantum theories, allowing stronger correlations, theories explaining wave function collapse, unification with consciousness, information theoretic, foundations, experimental possibilities, detection of quantum gravity, effects, discovery of quantum mechanics, violations, observation of extra dimensions, contact with post-quantum physics. The ultimate questions remain. Despite our quantum journey, fundamental questions persist. Why quantum? Why does nature use quantum mechanics rather than classical mechanics, or something else? Why these rules? Why Born rule for probabilities? Why complex numbers? Why Hilbert spaces? Why observer dependence? Why does observation play special role? What constitutes observation? Why 3 dimensions? Why 3 spatial dimensions? Are others hidden or emergent? Why consciousness? How does consciousness arise from quantum processes? Does it? Why existence? Why does anything exist rather than nothing? Is existence quantum? These questions might await revolutionary insights, surpassing quantum mechanics itself. Quantum mechanics gives us the gift of fundamental mystery, not temporary ignorance awaiting solution, but mystery that might be irreducible. The universe isn't a puzzle to solve but a mystery to experience. This mystery isn't frustrating, it's liberating. It means reality is richer than we imagined. Discovery will never end. Wonder is justified. Humility is appropriate. Possibility remains infinite. Understanding quantum mechanics transforms how we see everything, from mechanical to participatory. Reality isn't clockwork but creative unfolding. We participate in, from separate to entangled. Everything connects to everything in ways transcending space and time, from determined to probabilistic. The future isn't fixed but probabilistic, open to influence. From objective to observational, reality depends on observation, perspective, context. From either or to both, and contradictions can coexist. Paradox is fundamental. This worldview shift is quantum mechanics' deepest gift. Quantum mechanics calls us to adventure. Adventure of understanding reality's strange nature. Adventure of building quantum technologies. Adventure of exploring consciousness. Adventure of questioning assumptions. Adventure of embracing mystery. This adventure has just begun. We're first generations. Knowing reality is quantum, future generations will go further, discover more, understand deeper, but we have privilege of being pioneers, explorers of quantum frontier. The final paradox. The more we understand quantum mechanics, the more mysterious reality becomes. Each answer reveals deeper questions. Each discovery opens new mysteries. Each application suggests new possibilities. This isn't failure, but success. A reality fully understood would be boring. A mystery that deepens with exploration is infinitely rich. Quantum mechanics shows us reality is inexhaustible. Always more to discover. Always reason for wonder. As we end this quantum journey, receive this quantum blessing. May you exist in superposition of all your possibilities, until observation collapses you into your best self. May you be entangled with all beings, feeling the connections that transcend separation. May you embrace uncertainty as fundamental, finding peace in not knowing. May you recognize yourself as observer and observed, creator and created. May you dance with paradox, finding truth in contradiction. May you tunnel through barriers that seem insurmountable. May your consciousness interfere constructively with reality. May you find the courage to measure what matters, knowing measurement changes everything. May you remember you're made of stars, organized by quantum mechanics into awareness. May you know yourself as quantum being in quantum universe, strange and wonderful beyond imagination. This exploration ends, but invitation continues. Continue questioning reality. Continue exploring mystery. Continue embracing uncertainty. Continue recognizing connection. Continue participating consciously. Quantum mechanics isn't just physics theory, but invitation to new way of being. Accept this invitation. Let it transform you. Let it open you to possibilities beyond classical limitations. Remember, you are quantum mechanics in action. Every moment, particles in your body exist in superposition, tunnel through barriers, entangle with universe. You are living proof that quantum mechanics isn't abstract, but immediate, not separate but intimate. The quantum revolution isn't just technological but consciousness revolution. We're awakening to reality's quantum nature, including our own quantum nature. This awakening has just begun. What will you do with this quantum knowledge? How will you participate in quantum reality? What possibilities will you explore? The universe awaits your observation. Reality awaits your participation. The quantum future awaits your contribution. Welcome to quantum reality. It's your reality. It's you. The observation continues.